Hello there, welcome to Chemistry Chapter 2, Lecture 3. This is the final lecture of Chapter 2. And in this lecture I'm going to work a couple of calorimetry problems for you. So hopefully you remember from the last lecture that we have our calorimetry equation. That's minus Q of the object is equal to the Q of the water plus the Q of the calorimeter, where Q is the heat. And we got to remember also that Q is equal to MC delta T. So to remind you what a calorimeter is, I just want to show you the picture from your textbook on page 54. So it's an insulated device. The ones that you have in your lab are styrofoam. You fill them with water. You know the mass of the water. You have a thermometer and you know the temperature of the water. And then you put in a hot object. You know the temperature of that hot object. In this case, it's just this cube of red here, but it's usually metal, and in your lab, it'll be a metal bolt. You heat that object up, and you put it in the water. The object will cool down, and the water will heat up some, and you will take the temperature of all of that, and then you can figure out a lot of things just by knowing how much did that hot object heat up the water. So that is the process of calorimetry. So let's work two of those problems. We're on page 60. You're going to need your notes. So we're going to just fill up this back page of notes on page 4. And in your book, and before I get started on the problem, if this video helps you, please consider buying me a coffee. It's at Ko-fi.com, which is a safe way to buy me a coffee just with a $3 donation. And you can use PayPal or Venmo, anything like that. And you can either, there's a link in the description box, or you can scan this QR code here. All right. So let's take a look at page 60. 2.9 says a calorimeter, and there we have the mass and the specific heat of that calorimeter, holds 100 grams of water at an initial temperature of 25.1 degrees C. A 43.2 gram piece of metal at 111 degrees Celsius is dropped into the calorimeter, and the final temperature of the water is 29.1 degrees C. What is the specific heat of the metal? So I've written down the calorimetry equation again here. So we want to know what the specific heat of the metal is. So we can't get the Q of the object right away because we don't know the specific heat of the metal. However, we do know everything we need to get the Q of the water and everything we need to get the Q of the calorimeter. So in lecture 2, we were able to ignore the calorimeter. But in these two problems today, we don't get to do that. Okay, so let's get the Q of the water. We know that's equal to MC delta T. So the mass of the water is 100 grams. The specific heat of water, remember, is 4.184. And then the change in temperature of the water, the final temperature, is 29.1. And then the water started at 25.1. So remember, change in temperature is equal to T final minus T initial. So that's a total delta T of 4 degrees C. All right, so we're just going to put those numbers in our calculator. All right, let's clear that out. We got 100 times 4.184 times 4. All right, that's 1673.6. joules. Okay, we're 1/3 done. So let's get the Q of the calorimeter. We know that's mc delta T. All right, the mass of the calorimeter is 9 grams. The specific heat of the calorimeter, 2.31. So that's just right in the problem there in parentheses. And then the final temperature and initial temperature of the calorimeter is the same as that of the water. So that's 4 degrees C. They're always the same. So same as the water. Okay, so you can see the calorimeter is not, this number is not going to be all that big. So it doesn't make a huge difference in the problem. That's why sometimes we get to ignore it. So that's 83.16 joules. Okay, so we have, now I'm going to rewrite this. Minus Q of the object is equal to the Q of the water, which was 1673.6 joules, plus the Q of the calorimeter 83.16 joules. All right, if you add those two numbers together, you get 1756.76 joules. So minus Q of the object is equal to 1756.76. So if we divide both sides by -1 to get rid of this negative sign here, then the Q of the object is negative 1756.76. That just means the object, when it cooled off, when it splashed into that water, when it cooled off, it lost, the negative means it lost 1756.76 joules of heat. All right, so now we can say, okay, the Q of the object is equal to mc delta T. All right, so we have negative 1756.76 joules, that's the Q of the object, is equal to the mass of the object, and it says that that is 43.2 grams. The specific heat we don't know. That's what we're going to solve for. And then delta T. Well, the final temperature of the object is the same as the final temperature of the water and the final temperature of the calorimeter. They all equalize to the same temperature. So that final temperature of everything, so if you look in the problem, it says the final temperature of the water is 29.1. That's the final temperature of the object as well. All right, excuse me, that'd be our second number. So our initial, let's see, T final, yeah, I'm sorry, 29.1. Our initial temperature of the object is 111 degrees C. Okay, so the object, we got 29.1 minus 111 is negative 81.9. So that just means this object, the water cooled it off 81.9 degrees. Okay, finally we're going to solve for C. This is the last step. And I'm going to bring the 43.2 and the negative 81.9 underneath the negative 1756.76. That's the algebra. We're going to divide both sides by these numbers. So C is going to be negative 1756.76 joules divided by 43.2 grams times I'm doing two sets of parentheses. That's not how we're going to do it in our calculator, but times negative 81.9 degrees C. All right, let me remind you the best way to put this in your calculator. All right, I'm not going to put the negatives in at all because the two negatives cancel. Okay, so let's not even put that in. 1756.76 divided by, left parenthesis, 43.2 times 81.9, right parenthesis. All right, that'll get your order of operations correct, and you have 0.4965. Let's round that up to 0.497. And the unit's joules on top, grams times degrees Celsius on the bottom. Don't forget the unit. You'll get counted off on the test if you do. So units are really important. All right, and we know that that is the unit for specific heat, so we know we did the algebra right. If you accidentally put this 1756.76 joules on bottom, if you got all this reversed, you'd have the wrong unit. You'd have grams times degrees Celsius over joules. So that helps you know, knowing what the unit should be, helps you know that you did the algebra correctly. All right, great. So let's do one more, and then you'll be an expert in calorimetry problems. Okay, we're going to do on your own 2.10 right beneath page 60. So we know it's a calorimeter problem. We'll just go ahead. I won't rewrite the equation. We're going to be using this equation. All right, 2.10 says a calorimetry experiment is performed with a calorimeter that has a specific heat of 3.77 joules over grams times degrees Celsius. The calorimeter has a mass of 9.5 grams filled with 117 grams of unknown liquid. So instead of water, we don't know what the liquid is. Okay, that is initially at a temperature of 25 degrees C. If a 50-gram chunk of copper at 112 degrees C is dropped into the calorimeter and the liquid's temperature increases by 2.3 degrees, what is the specific heat of the unknown liquid? All right, so they didn't give us the final temperature here, but we can figure it out. Okay, so we want to know what's the specific heat of the unknown liquid. So we can't get the Q of the liquid or the Q of the water here, so I'm going to put a question mark there. We have everything we need to get the Q of the object, in this case 50 grams of copper, and everything we need to get the Q of the calorimeter. So let's go ahead and calculate those. The Q of the object, that's MC delta T. That is a 50-gram chunk of copper. So the copper, we'll have to look back in our book at the table to see what the specific heat of copper is. It's 0.3851. So you might have to look in your book. That's on page 50. And then the change in temperature. So remember, everything ended up at 27.3 degrees Celsius. How do I know that? So that's the final temperature, T sub F. And I'll show you how I figured that out in a minute. And then the copper started out at 112 degrees. That was our T initial. Okay, so the way that I know it is that the water, so T final, the water started out at 25 degrees Celsius, and it was raised by 2.3 degrees Celsius. So that's just from the problem. So that's 27.3 degrees Celsius. So that's how I got that final temperature. All right, so the Q of the object is 50 times, in fact, let's go ahead and do the 27.3 minus 112. So that's negative 84.7. All right, that makes sense because the object's cooling down, so it's going to have a negative change in temperature. All right, so we've got, let's try this again, 50 times 0.3851 times negative 84.7. All right, that's negative 1630. Negative 1630. We'll round that to 0.9. So it's 0.898, so 0.9 joules. All right, that's the Q of the object. So we're 1/3 done. Let's get the Q of the calorimeter. We know that's equal to mc delta T. The mass of the calorimeter is 9.5 grams. The specific heat of that is 3.77, just right from your problem. All right, and then the change in temperature. Remember, the whole thing raised 2.3 degrees. Okay, that was just right from the problem. The change in temperature for the calorimeter and the water is exactly the same, so that'd be 2.3 degrees C. So if the water goes up by 2.3 degrees, the calorimeter also goes up by that amount. So 9.5 times 3.77 times 2.3. So that's 82.4 joules. Okay, now we can get the Q of the unknown liquid. All right, I'm calling it water, but the unknown liquid. So I have minus Q of the object. So that would be minus 1630.9 joules. Remember, the Q of the object's negative, but we have minus Q of the object. So minus is equal to Q of the water plus the Q of the calorimeter, 82.4 joules. So two negatives make a positive. So we've got 1630.9 joules. And then if we subtract 82.4 from each side, minus 82.4 joules, that's equal to the Q of the water. We're going to subtract 82.4, subtract 82.4. All right, so the Q of the water, if you subtract those two, is 1548.5 joules. All right. So we're almost done. Now, we've got the Q of the water, or the unknown liquid. We know that the Q of the water is equal to mc delta T. We're trying to get C. So 1548.5 joules is equal to the mass of the water. All right, look back at the problem. That's 117 grams. We don't know the specific heat. That's what we're trying to get. Not always trying to get that. Sometimes, we're solving for the mass or the delta T. Okay, but in these problems we've been solving for specific heat. But the algebra is the same. And then delta T, we figured out a little earlier, 2.3 degrees C. Right? That's given in the problem. The change in temperature of the water heated up by 2.3 degrees C. So we're going to bring the 117 and the 2.3 underneath 1548.5. Okay, we're almost home free. Okay, so we've got 1548.5 divided by left parenthesis. If you forget this parenthesis, it's going to give you the wrong answer. 117 times 2.3 right parenthesis. That's 5.75 joules over grams times degrees Celsius. Don't forget the unit. So this has a specific heat, this liquid, of a little more than water. Okay, so it's a little harder to heat up than water. Okay, your homework from this section are just the last two practice problems. So practice problems on page, so we've got page 68. You can finish those up, do 9 and 10. You got two calorimeter problems. You get to ignore the calorimeter in 9, so that one will be a little bit shorter. And then in 10, you don't get to ignore it, so it's a little longer problem like this. All right, great. So as has been my my custom on the last few videos, we'll do a guitar play out song, and I hope you have a great day. That was a little rough. Sorry about that. See ya.